Somewhere in the southern sky, a point of light flared into existence, burned for a matter of hours, and then vanished completely, leaving behind nothing. No star at that location before it happened. No galaxy, no known object of any kind, sitting at those coordinates either before the flash or after it faded. Just a brief, unexplained burst of light, captured by the newest and most powerful survey telescope ever built, and then gone, as if it had never happened at all, leaving behind nothing more than a single entry in an automated database and a question mark where a proper scientific explanation should eventually go. This isn't a one-time fluke. It's happening regularly right now as the Vera C. Rubin Observatory, barely months into full operation, sweeps across the sky night after night, and every so often, buried inside the hundreds of thousands of automated alerts it generates, sits an object that professional astronomers, using the exact same tools and the exact same catalogs that correctly identify almost everything else in the sky, simply cannot explain. Astronomers actually have a name for these objects. They call them orphan transients, events with no known parent, no host galaxy, no prior identity, nothing connecting them to anything else in the observable universe except the brief flash of light itself, a label that, once applied, immediately marks the object as a priority for any research team paying close attention to the incoming alert stream. And with Rubin's 10-year survey only just beginning, the number of these unexplained detections is about to increase dramatically, from a scattered handful found over the past decade by earlier, smaller surveys, to potentially dozens or more discovered every single year. Stick around, because by the end of this video, you'll understand exactly what these mysterious appearing and disappearing objects actually are, why some of the leading theories sound almost as strange as the phenomenon itself, and why astronomers are racing right now to build automated systems fast enough to catch these things before they vanish for good. And if you want to see what Rubin catches next, because this observatory has barely gotten started, subscribe now, because we'll be covering every strange new detection as it happens. There's a certain fitting symmetry to the fact that an observatory named after Vera Rubin herself is the one turning up this specific kind of mystery in such large numbers. Rubin, the astronomer this facility is named for, spent much of her career in the mid-20th century carefully measuring the rotation speeds of stars orbiting within distant spiral galaxies, and found something that didn't match what the visible matter in those galaxies could explain on its own. Stars far out at a galaxy's edge, orbiting just as fast as stars much closer to its center, a pattern that made sense only if a large amount of additional, completely invisible mass was distributed throughout each galaxy, exerting real gravitational influence while emitting no detectable light of any kind. That observation became one of the strongest pieces of early evidence for the existence of dark matter, a substance that, decades later, still cannot be directly detected by any instrument humanity has ever built, studied instead entirely through its gravitational effects on the visible matter around it. An orphan transient represents, in a strange and very different way, a similarly indirect kind of mystery, a real, physically confirmed event. Verified by multiple independent measurements and a reliability score, astronomers trust completely, with an underlying cause that, for now, remains just as invisible and just as unconfirmed as the dark matter Rubin spent her career chasing evidence for. To understand why an orphan transient is such a genuine puzzle, you first have to understand how the Vera Rubin Observatory actually works, because it operates on a fundamentally different principle than most telescopes built before it. Rather than pointing at one specific target and studying it in careful detail, Rubin, perched atop Cerro Pachon in the Chilean Andes, is designed to photograph the entire visible southern sky over and over again, roughly every 3 to 4 nights, for a full decade, using a camera the size of a small car, containing 3.2 billion individual pixels, the largest digital camera ever built for astronomy, mounted on an 8.4-meter telescope specifically engineered to move quickly enough between exposures to cover that much sky on such a demanding schedule. This repeated, systematic imaging campaign, formerly called the Legacy Survey of Space and Time, officially began on June 30th, 2026, after the observatory spent the previous year running test observations and refining its systems, following first light in June of 2025. The entire point of observing the same patch of sky again and again, rather than just once, is to catch change. Every time Rubin photographs a region of sky, its automated software immediately compares the new image against a carefully built reference image called a template, showing what that same patch of sky normally looks like. Anything that's different between the new image and the template, a point of light that wasn't there before, a source that used to be there and suddenly isn't, or an object that's simply changed in brightness, gets automatically flagged and sent out as an alert within minutes, available to astronomers and automated systems anywhere in the world almost in real time. On February 24th, 2026, during an early test of this alert system, Rubin sent out 800,000 individual alerts in a single night. And once the observatory reaches its full operational cadence, that number is expected to climb dramatically, with some estimates suggesting Rubin could eventually generate close to 10 million alerts every single night across its full 10-year survey. Most of those millions of nightly alerts, overwhelming as the sheer number sounds, actually get explained fairly quickly and fairly easily by automated software. The vast majority of changes Rubin detects turn out to be asteroids drifting slowly across the frame between exposures, variable stars pulsing predictably in brightness the way they always have, active galactic nuclei flickering as material spirals into a supermassive black hole at a galaxy's center, or supernovae exploding inside galaxies that were already sitting there, cataloged and well understood, before the explosion ever happened. Automated matching software with names like Sherlock cross-references every single alert against enormous existing catalogs of known galaxies, stars, and solar system objects. And for the overwhelming majority of detections, that matching process works cleanly, immediately connecting a flash of light to a known, sensible, physically understood source. But every so often, that matching process comes back with nothing. No catalogued galaxy sits anywhere near the transient's position, even in the deepest, most sensitive existing imaging surveys available. No known star, no known asteroid, nothing on record anywhere close to those exact coordinates. The transient simply appears, unconnected to anything astronomers have ever previously detected in that specific patch of sky. And when that happens, the automated classification software has a specific label reserved for exactly this situation. It calls the object an orphan. One person working directly with Rubin's alert data captured what this actually looks like in practice in a detailed public account posted in March of 2026, describing the experience of connecting to one of Rubin's public alert brokers, a UK-based system called Laser, and setting up a basic filter to watch for interesting events, a process that took nothing more than a standard web browser and a free account to get started with. Within a relatively short window, an alert came through flagging exactly this kind of object, a source with a reliability score close to the maximum possible value, meaning the automated system was almost completely confident this represented a genuine astrophysical event rather than a processing artifact or instrument glitch. And yet, once every available parameter had been checked, the object couldn't be confidently matched to a galactic nucleus, a supernova, or any other established class of astronomical object at all. A real, confirmed burst of light had occurred. Its actual origin remained, and still remains, genuinely unknown. It's worth understanding exactly how an ordinary person, without any formal astronomy credentials, can actually access this kind of live data at all, because that access is a deliberate, built-in feature of how Rubin's entire alert system was designed from the ground up. Rather than keeping its nightly flood of detections locked away for exclusive use by a small circle of professional research teams, Rubin distributes its full alert stream in real time to a network of independent organizations called brokers, each one built by a different combination of universities and research institutions, specifically to help astronomers, and in many cases genuinely curious members of the public, sort through the overwhelming volume of nightly detections. Laser, developed through a partnership between the University of Edinburgh, Queen's University Belfast, and the University of Oxford, is one of several of these brokers, alongside others including Vera C, Fink, and Antares, each maintaining its own filtering tools, its own website, and its own set of automated classification, systems layered on top of the same raw alert stream flowing out of Rubin every single night. The same open alert infrastructure has already produced genuine scientific contributions from outside the traditional professional research pipeline entirely. Early in Rubin's operational history, astronomers working with the observatory's solar system team confirmed more than 11,000 previously unknown asteroids from preliminary survey data alone, including several unusually fast-spinning objects that immediately raised their own separate set of questions about how solid, rocky bodies that size could physically hold themselves together while rotating as quickly as they do. That same open, publicly accessible pipeline is exactly what allowed the orphan transient described earlier to be flagged and investigated by someone working entirely outside a formal university research program, using nothing more than a web browser, a free broker account, and enough patience to sit and watch the alerts as they arrived. This is not, in itself, some brand new phenomenon that appeared out of nowhere the moment Rubin switched on. Orphan transients have been quietly turning up in smaller numbers for years, thanks largely to Rubin's most important direct predecessor, the Zwicky Transient Facility, a smaller but still highly capable survey telescope that has been systematically scanning the sky since 2018 and pioneered much of the automated alert infrastructure Rubin now builds directly on top of. Over the years, since ZTF began operating, astronomers have confirmed roughly 10 genuine orphan afterglows through that survey alone, each one published individually because each one represented a significant enough discovery to warrant its own dedicated research paper. One of the clearest, most thoroughly documented examples is a transient cataloged as AT2021 ANY, discovered on January 16, 2021 at 6:59 in the morning, just 22 minutes, only the tail end of one of the most violent explosions known to occur anywhere in the universe. Gamma-ray bursts, the extraordinarily energetic explosions produced when a massive star collapses, or when two extremely dense stellar remnants collide and merge, don't release their energy in every direction evenly. Instead, they typically fire off in two narrow, tightly focused jets of radiation, blasting outward from the explosion's poles like a cosmic lighthouse beam rather than spreading out in a sphere. If Earth happens to sit directly in the path of one of those narrow jets, gamma-ray telescopes detect an unmistakable, extremely bright burst of high-energy radiation, exactly the kind of event that gets studied and cataloged as a confirmed gamma-ray burst. But if Earth is even slightly off that narrow beam's path, missing the initial jet entirely, the extraordinarily bright gamma-ray flash itself passes by completely undetected. What can still reach Earth, however, is the afterglow, the slower, much wider, much less directional glow produced afterward as the explosion's outward-moving material collides with and decelerates against the surrounding interstellar gas, spreading the visible light out across a far broader angle than the original narrow jet ever covered. In that specific scenario, astronomers never see the explosion itself happen. They only ever catch the widening, fading afterglow arriving days, hours, or sometimes just minutes later, with absolutely no warning, no initial trigger, and, critically often, no visible host galaxy either, especially if the explosion occurred in a faint, distant, or unusually dark region of its home galaxy that existing deep imaging surveys simply weren't sensitive enough to detect. Researchers studying this specific phenomenon, working from theoretical models published years before Rubin ever began construction, had already predicted the Future Legacy Survey of Space and Time could detect roughly 50 of these so-called orphan afterglows every single year from long-duration gamma-ray bursts alone, a number that dwarfs the roughly 10 total examples confirmed across the entirety of ZTF's multi-year survey up to this point, a gap that itself illustrates just how much detection power a survey the scale of Rubin genuinely represents compared to everything that came before it. But gamma-ray burst afterglows caught off axis are only one proposed explanation among several, and not every orphan transient necessarily fits that specific model cleanly. Astronomers studying houseless events more broadly have identified several other categories that can plausibly produce a flash of light with no visible parent galaxy attached. Some supernovae genuinely do explode far out on the extreme edges of their host galaxies, at distances faint and diffuse enough that existing imaging surveys simply fail to detect the host at all, even though a real physical galaxy is technically there. Studies specifically measuring this effect across several major transient surveys have found that somewhere between roughly 1.5% and 4% of all detected supernovae end up formally classified as hostless for exactly this reason, a small but genuinely persistent fraction of essentially every major survey's total detections, consistent enough across multiple independent surveys conducted over different years and using different instruments that researchers now treat it as a reliable, expected baseline rather than a statistical fluke. Tidal disruption events produced when a star wanders too close to a supermassive black hole and gets torn apart by extreme gravitational forces can also occasionally appear disconnected from any obvious host if the surrounding galaxy is unusually faint or compact. And an entirely separate, still poorly understood category known as fast blue optical transients, extremely rapid, intensely luminous flashes that rise and fade within days rather than the weeks or months a typical supernova takes, remain genuinely mysterious, even in cases where a host galaxy is clearly visible, with astronomers still actively debating exactly what physical process produces them at all. What makes Rubin fundamentally different from every survey that came before it isn't that it's discovering an entirely new category of phenomenon nobody had ever previously detected. It's the sheer, overwhelming scale at which it's now capable of finding these events. The Zwicky transient facility, working at its full operational capacity, generates somewhere in the range of a few 100,000 transient alerts on a typical night. Rubin, once its 10-year survey reaches full operational pace, is expected to generate somewhere close to 10 million alerts every single night, a jump of well over an order of magnitude in raw detection volume. If orphan transients represent even a small, consistent fraction of that dramatically larger total, and there's no obvious physical reason they wouldn't, the sheer number of genuinely unexplained flashes waiting to be caught, studied, and hopefully someday properly classified is about to increase dramatically, potentially by a very similar order of magnitude, transforming what has been a slow, painstaking process of confirming roughly one new orphan afterglow per year into something considerably closer to a routine, ongoing discovery pipeline. That kind of scale, though, creates its own entirely separate problem, one that has nothing to do with physics and everything to do with logistics. Eric Bellum, who leads the alert production pipeline group for Rubin's data management team at NSF Noir Lab and the University of Washington, has explained that Rubin's entire alert system was specifically designed to give astronomers enough advance notice to organize rapid, time-critical follow-up observations using other telescopes around the world, because many of these fast-fading transients, orphan afterglows especially, only remain bright enough to study in real detail for a matter of hours before they fade below what most instruments can detect at all, with millions of alerts pouring in every single night, manually reviewing each one individually to determine which handful genuinely deserve that kind of urgent, resource-intensive follow-up simply isn't possible for any team of human researchers, no matter how large. That specific bottleneck has driven a wave of new automated software specifically built to solve it. Systems with names like Elephant, a purpose-built pipeline for automatically filtering hostless transients out of massive incoming alert streams, and anomaly detection modules built into broker platforms like Think, are being actively developed and refined throughout 2025 and 2026 specifically to comb through Rubin's flood of nightly alerts in real time, automatically flagging the small subset of genuinely hostless, genuinely unclassifiable events before they fade past the point where any follow-up telescope could still catch them. Work that requires constant tuning as researchers learn more about which combinations of brightness, color, and fade rate actually correlate with a genuine orphan event rather than a simple instrumental artifact. Separate research teams have also started building cross-referencing systems that pull in data from other major sky surveys, including the European Space Agency's Euclid Space Telescope, specifically to check whether a transient Rubin flags as hostless might actually have a faint host galaxy visible in a different survey's deeper or differently filtered imaging, since a host too faint or too red for Rubin's specific instruments to catch cleanly might still show up clearly in another. Telescope's data, gathered through an entirely different set of filters and a different level of sensitivity. Sit with what that actually means for a moment, because it reframes the entire situation in a genuinely interesting way. This isn't primarily a story about astronomers being stumped by some entirely unprecedented, physics-breaking phenomenon nobody has any theoretical framework for at all. Researchers already have several serious, scientifically grounded candidate explanations on the table, off-axis gamma-ray burst afterglows chief among them, backed by real theoretical predictions published years in advance of Rubin's survey actually beginning. What's genuinely new and genuinely challenging is the sheer scale and speed at which Rubin is now capable of finding these events, combined with the extraordinarily narrow window available to actually study any individual example in enough detail to confirm which specific explanation applies before it simply fades away and becomes permanently unrecoverable. Every orphan transient Rubin detects, and nobody manages to follow up on quickly enough, represents a genuine, permanently lost opportunity. A flash of light from some specific, physically real event, possibly a gamma-ray burst jet that happened to miss Earth by the narrowest of margins, possibly something else entirely that doesn't fit any existing model at all, gone forever the moment it fades below detection, with no second chance and no way to ever go back and study it again. That last possibility, that at least some fraction of these orphan detections might not fit any existing theoretical model at all, is exactly what makes this particular corner of Rubin's early science genuinely exciting, rather than simply a logistical challenge to be managed. Every major new survey telescope in the history of astronomy that has dramatically increased humanity's ability to detect faint, fast-changing events in the sky has, sooner or later, turned up at least a handful of genuinely novel phenomena that didn't fit into any pre-existing category at all. Fast radio bursts, certain classes of luminous, fast blue transients, and repeating tidal disruption events all trace their initial discovery back to exactly this kind of unexpected, difficult to classify detection, showing up in survey data that wasn't specifically designed to look for it, often sitting unnoticed in an existing archive for months or years before anyone realized what they were actually looking at. With Rubin now generating orphan transient candidates at a rate that could plausibly reach dozens or more per year, rather than the roughly one per year that earlier surveys managed to confirm, the statistical odds of catching something genuinely new, something that doesn't fit neatly into the off-axis gamma-ray burst model or any of the other established hostless transient categories, climb substantially higher than they've ever been before in the history of this specific kind of astronomy. A shift researchers involved in building Rubin's follow-up infrastructure have openly described as one of the most exciting aspects of the survey's early years. Right now, in the summer of 2026, Rubin's full 10-year survey has only just begun, having formally started on June 30th, following more than a year of careful testing, calibration, and operational review after the observatory's first test images back in June of 2025. The observatory is still, in a very real sense, just getting started, with the overwhelming majority of its planned decade-long survey and the overwhelming majority of the orphan transients it's statistically expected to eventually catch, still lying entirely ahead of it. Every night that passes adds another round of hundreds of thousands and eventually millions of fresh alerts to an already enormous and rapidly growing dataset, and buried somewhere inside that flood, on a fairly regular and predictable basis, if the existing theoretical predictions hold up, sits another flash of light with no obvious origin, no cataloged host, and only a brief, narrow window of time in which any telescope on Earth could possibly gather enough additional data to figure out what it actually was before it fades away for good. If you want to see what Rubin catches next, and you want to actually understand it properly when it happens, rather than getting a vague, oversimplified headline stripped of the real science behind it, subscribe now and turn on notifications, because this observatory has generated more raw data in its first several months of operation than most entire surveys managed across their full multi-year lifetimes. And the genuinely strange detections, the ones nobody can fully explain yet, are only just beginning to show up in meaningful numbers. Somewhere out there right now, in a patch of sky Rubin hasn't photographed yet tonight, something is very likely about to flare into existence, burn for a few brief hours, and then disappear completely. And whether anyone manages to figure out exactly what it was before it's gone depends entirely on how fast the automated systems built over the past year can flag it, and how quickly a real telescope, somewhere on Earth, can turn to look. Rubin's own namesake spent a career chasing evidence for something she could never directly see. A decade from now, this observatory may end up doing exactly the same thing for a phenomenon nobody has fully named yet either.